Good day everyone and welcome to our next lesson. In this session, we will embrace two concepts in the field of combinatorics, the concept of permutation and combination. For our learning objectives, by the end of this lesson, you should be able to determine whether order matters or does not matter in a situation, in order to identify whether a problem is a permutation or a combination. Alright, so here's a short history of permutation and combinations. Ancient scholars in India and China use counting methods similar to permutations. So before the formulas of permutation and combination appeared in modern textbooks, ancient scholars were already thinking about how many ways things could be arranged. In ancient India, the scholar Pingala studied poetic meters. He asked questions like, in how many ways can long and short syllables form a verse? Meanwhile, in ancient China, mathematicians asked practical questions about how to arrange soldiers, how to distribute grain, or how to display signal flags during military campaigns. These counting problems helped them think systematically. They weren't just doing math, they were organizing life itself. So whether it was troop formations, dividing harvest, or creating verses, people were already exploring what we now call permutations and combinations thousands of years ago. And then in the 7th century, Leibniz studied arrangements and order of numbers, or what we call as permutation. And then later, Pascal explored counting without order, or we call it combination, through the binomial theorem. I hope you have watched the video entitled Combinatorics in Binomial Theorem. So these led to the formal study of combinatorics, the mathematics of counting. So what is a permutation? Permutation refers to the arrangement of objects or symbols where the order matters. So here's the formula for permutation. We will not be discussing in detail the computation part for now. We will do so in another video. In this session, we will just be identifying whether the situation is a permutation or a combination. So here's an example of a situation where order matters. Hence, it involves the permutation operation. So the order of metals, gold, silver, bronze, such order matters, right? So now, what is a combination, or when is it a combination problem? A problem or situation is a combination problem when the order does not matter. So example, when we're going to choose 3 classmates for a team, order doesn't matter. Why? Because choosing Anna, Kathy, Diane, or choosing Kathy first, Diane next, and Anna last, the combination remains the same. We have chosen 3 girls, Anna, Kathy, and Diane. So order doesn't matter. Alright, so here are examples of permutation problems or the order matters. So problem number 1, arranging 3 books on a shelf from 5 available books. Write the given. How many books are there all in all? So we have 5, so n is equal to 5. How many books will be arranged properly on the shelf in a particular order? 3 books. So R is equal to 3 or K is equal to 3. So the keyword here is arranging. And this is permutation because the order of book matters. Science, math, chemistry arrangement is different from chemistry, science, math arrangement. And here is a sample computation for this. We will break down the computation process in another video lesson. Alright, so example number 2 for permutation, sitting 4 students in a row from 6 total students. So how many total students are there to be seated? 6. So n is equal to 6. How many students would be arranged in a row? 4. So k is equal to 4, r is equal to 4. So the keyword here is sitting. And why permutation? Because the position of each student matters. Alright, so example number 3 for permutation, creating a 3-digit pin from 0 to 9 without repetition. So given, how many digits to choose from. Since the 3-digit PIN would be either 0 to 9, then we have 10 digits to choose from. So N is equal to 10. How many digits for the PIN code? Only 3. So K or R is equal to 3. So the key word here is code. So order matters. So why is it a permutation? Again, order matters in a code. The code 123 is not the same as code 321. Order changes the PIN, right? So this is a permutation problem. Right, so example number 4, permutation, choosing a president, vice president, and secretary from 8 members. Alright, so how many members to choose from? That's 8. So N is equal to 8. And then how many members to be chosen out of the 8 members? 3. Okay, so R is equal to 3. And then for position, order matters. So president, highest, next vice president, next secretary. So there is ranking there. Okay, again, this is permutation because each position is distinct. President, vice president, and secretary. So order matters. Alright, so example number 5 for permutation, deciding the top 3 finishers in a race of 10 runners. So how many runners are there? 10. So N is equal to 10. How many top finishers are we going to have? Only 3. We're going to have top 3 finishers, so R is equal to 3. So the keywords here, there is the ranking, and this is permutation because the rank first, second, third are not interchangeable, so order matters. So next example for permutation, arranging letters A, B, C, or D into 2-letter words. So how many letters to choose from? 4. A, B, C, or D. So N is equal to 4. And then, how many letters do we need to form a word? 2. Okay? There should be only 2 letters in a word. Alright? So R is equal to 2. Okay? So this is permutation because of the keyword arrangement. Okay? So reason again, the arrangement AB is not the same as the arrangement BA. Another example for permutation, creating a 3-digit locker code from 5 numbers. So how many numbers to choose from? 5. So N is equal to 5. And then how many digits for a locker code? 3 only. So we're going to choose 3 digits from 5 numbers. So R is equal to 3. So keyword, code, and the order matters. So the reason, the code 123 is not the same as the code 321. Right, so example number 8 for permutation, problem selecting the first, second, third place winners among 12 contestants. So how many contestants are there all in all? 12, so N is equal to 12. And how many winners are we expecting to have? 3, so R or K is equal to 3. And this is permutation because of the keyword ranking. Reason, different ranks produce different outcomes, so order matters. Alright, so now for the combination problems. Example number 1, choosing 3 students from A to join a team. So N is equal to 3. There are 8 students all in all. And we're gonna choose only 3 students. So R is equal to 3. Keyword selection. So order doesn't matter. So what are we doing again? We're selecting students. Does order matter? No. Why? Because the team remains the same regardless who is named first or last. Example number 2 for combination, selecting 4 toppings out of 10 for a pizza. So how many toppings are available? 10. So N is equal to 10. But how many toppings can we choose? Only 4. So R is equal to 4. So the keywords here, combination, selection, right? So what are we doing? We're choosing toppings. Does order matter? No. The pizza tastes the same regardless the order. Reason, it is a combination problem because the choice of ingredients doesn't depend on order. Now for the third example for combination problems, Picking 3 cards from a deck of 52. So how many cards in a deck? 52. So n is equal to 52. And out of 52 cards, how many are we going to pick? 3 cards only. So r is equal to 3 or k is equal to 3. So the keywords, draw or picking. So again, what are we doing? We are drawing cards. Does order matter? No, the hand is the same regardless of the draw order. Reason, the order of drawing does not change the combination of cards. And now for example number 4, combination problems. Picking lotto numbers 6 out of 42. So how many lotto numbers all in all? 42. So n is equal to 42. But how many numbers are going to pick out of 42? Only 6. So r or k is equal to 6. So the keywords, lotto or picking. What are we doing? We're choosing numbers. So does order matter? No. The set is the same regardless of the draw order. Reason, this is a combination problem because the order of the numbers doesn't change the chosen set or the winning set. Now let's keep track of the summary of keywords. For column 1, it is a permutation problem when the order matters. And the problem situation has either of the following keywords: arrangement, order matters, rank or position, code or pin, sequence, placement, arrangement of seats, winning order or race result. And now for column 2, we have the combination problem when the order does not matter. And the order doesn't matter when the problem or situation has either of the following keywords: selection, order doesn't matter, choose, pick, group, committee, team, collection, choice of flavors or toppings, membership, or group composition. Alright, it's now your turn to discover and explore. Try this. Please determine whether the situation involves a permutation operation or combination operation. So please pause the video and answer section 6. Alright, so that's the end of the session. See you in our face-to-face session. Stickers and badges are up for grabs. So let's continue finding joy in learning mathematics through both ancient wisdom and modern applications.